Hello again, physics friends. We have already seen for our two-state system two properties, color and hardness. Color can take on two values, blue and white. Hardness can take on two values, hard and soft. And we've seen and used color boxes and hardness boxes in various configurations to look at repeated measurements, incompatible observables, and so on. And one of the main takeaways from our last conversation was that if you measure the same property twice in a row, like color and then color, you're going to get the same outcome on the second measurement. But if you interleave a hardness measurement in between two color measurements, then it's as if the first color measurement never happened. The measurement of hardness destroys the information about color. And in particular, after the hardness measurement, there is no defined color for the particle. So that's interesting. And what we want to focus on today is this idea of an interferometer made out of a hardness or a color box. And we want to really get at what this idea of measurement means. Okay, so we're going to introduce a new tool, a new device. Here we'll call it the hardness interferometer. And our hardness interferometer is going to have a few features. And we can see here several of them right off the bat. First of all, at the core of the hardness interferometer is the hardness box. So we still have one input and two outputs. So you shoot in an electron, and that electron will either come out of the hard port or the soft port. So you're guaranteed that the electron will exit the hardness box. Okay. Now we've introduced a couple new items, a mirror and a merger box. And we can talk about the two branches through the interferometer, the hard branch and the soft branch. Okay, so the goal here basically is to have one input and one output. Notice that's different than a hardness box, which has one input and two outputs, right? And the location of the output tells us about the value of that property. So if it comes out the top, that electron is hard. If it comes out the side, that electron is soft. But here there's only one output, okay? But there's two ways through the interferometer. Now this should make you think of the two-slit experiment, right? So if you remember, we have a source and two slits and then a distant screen, and pick a point on that screen, okay? You can get to that point by either going through slit 1 or slit 2, and if we're not measuring what slit was taken, in other words, if both slits are open and we don't have a device that can sense a quanton going through a specific slit, then we do not have which way information, and that means that we're going to get interference effects. We're going to get wave-like behavior for those quantons. So in the absence of which way information, those quantons behave as if they're in a wave-like way. We can also talk about the same thing with the interferometer. So the interferometer scrambles which way path information, because whether a particle came out the H or the S port, we don't know. All we know is that it came out of this merger box. Okay, so we have an electron come in. The properties, the value of the hardness property is mapped onto some spatial position, right? So hard is up and soft is right. But these mirrors reflect the hard and reflect the soft electrons, bring them to a merger box where they're redirected out to the right. And this interferometer has now scrambled the which way information. So if we put our eyeball here and we count the number of particles coming out, we do not know which route was taken. Okay. Now these mirrors it's important to know that this mirror does not alter in any way the properties of the electron. Okay, so all it does is redirect them. And the same goes for the merger box. So what actually is the merger box doing? Well, if an electron is coming into the merger box from the left side, then that electron just passes through with no effect. Nothing is done to that electron, it just passes straight through. If the electron enters the merger box from below, then the merger box acts as if there's a mirror inside that reflects the electron to the right. Okay. So in this current configuration, if we see an electron at the output, we have no information about which path was taken through the interferometer, and therefore which port H or S that electron left out of the hardness box. All right, so I just want to do a quick check-in for us. What does an electron mirror do? In other words, if we shoot electrons into this hardness box and 100 of them exit the H port, reflect off this mirror, and we put them into another hardness box, what are we going to expect to see? Would they all come out H? Would they all come out S? Would some come out of H and some come out of S? Okay. So pause and figure out an answer to this and justify your answer. Well, the way I think about this is that we are told a mirror does not affect the state of the electron in any way. So this is a repeated measurement of hardness. And we know that for repeated measurements of hardness or repeated measurements of color, the outcome of the second measurement is 100% predictable. So if we know that the electron exited the H port of the first hardness box, then we are guaranteed that this electron will exit the H port of the second hardness box. So the distribution of values will be 100 and 0. In other words, the mirror is just there to redirect the particles, but it does not change the state of those electrons. Okay, good. So we have an understanding of what the mirror does and does not do. How about the merger box? So here we have a simplified setup where we have our hardness box that takes input electrons. Those electrons are going to reflect off the mirror. We know that they don't change their state. They enter a merger box. And if we remeasure hardness, what are we going to expect to see? Well, we can see here that we're shooting 100 hard electrons in. So 100, all of them will take the upper leg, reflect off the mirror, and enter the merger box. None of them will exit the soft port here. Okay, so we're going to have 100 here and 0 here. So the 100 electrons reflect off the mirror, and they just go right through the merger box. Their state is unchanged. And if their state is unchanged, that means that 100 of them will exit the H port and 0 of them will exit the soft port. So the H comma S will be 100 comma 0. Okay, pretty straightforward stuff. The merger box and the mirror just serve to redirect the motion of the quantons, or the electrons in this case. They do not change the state of the electron in any way. Don't change its hardness state, and don't change its color state. And just to be really explicit and clear here, we can ask the same about the merger box for soft electrons, which take the lower path. If we shoot 100 soft electrons into this apparatus, none of them will exit the H port. All of them will exit the S port. They will reflect off of the mirror and travel upwards into the merger box. And for these electrons, the merger box just acts like another mirror at 45 degrees that will reflect the electrons to the hardness box. When we then make a subsequent measurement, this is simply a repeated measurement of hardness. And so we know that if all of the electrons at the input were soft, then all of them will exit the soft port of the second hardness box. So this experiment is exactly the same as experiment 1 from last class. If you do a repeated measurement of hardness, you're going to get the same outcome the second time. Okay, now that we've introduced a hardness interferometer, let's use it to build a new experiment. And we'll call this experiment number 4. We're sending white electrons into a hardness interferometer, and then we're going to measure hardness at the output. Okay, so this is again straightforward. We shoot white electrons in, and we measure hardness at the output of the interferometer, and what we find is 50 hard and 50 soft. So let's try to explain two possibilities for this, and I'll call one possibility the mixed state possibility and the other the superposition state possibility. So we'll make this a little bit smaller to give us some more space to write and do our analysis, and here we go. Okay, we'll start with the so-called mixed state explanation, and it's called a mixed state because this explanation, which by the way turns out to be incorrect, although it sounds very reasonable. This explanation says that when entering the final hardness measurement, every single electron has a defined hardness state because it has already gone through a hardness box. Okay, and it's saying, okay, we have 100 white electrons that come in. We know that if you have a white electron in a hardness box, you have a 50-50 chance of coming out hard or coming out soft. So that means 50 electrons take the upper branch and arrive at the second hardness box in the H state, the hard state. The other 50 electrons will have taken the soft branch and will arrive at the hardness box in the soft state. The 50 hard electrons will all exit the H port, and the 50 soft electrons will all exit the soft port. And that explanation seems perfectly reasonable because here it looks like we're making a measurement of hardness at the entrance to the interferometer, and we know that a repeated hardness measurement is guaranteed to give the same result. Okay, so this explanation sounds very reasonable. Okay, it also is incorrect. So how is it that something that sounds so reasonable is still incorrect? Well, let's see. I'm going to put up a second explanation that I'll call the superposition state explanation, and we'll see that it predicts exactly the same outcome. Okay. So the superposition state argument, which turns out to be correct, even though it sounds bizarre and outlandish, states that any single electron that enters the final hardness box does not actually have a defined value for hardness. It's in a superposition of hard and soft. And so when it enters this hardness box, any one given electron has a 50% chance of emerging from the H port and a 50% chance of emerging from the S port. So both of these explanations, okay, they both predict 50 hard and 50 soft electrons. So this data set that we have, this experiment number 4, cannot distinguish between these two models, okay? We'll do subsequent experiments and show that indeed the superposition explanation is correct and different from the mixed state explanation, and that the superposition state explanation works in all of these cases, whereas the mixed state explanation does not. So you might be wondering, well, why in God's name would this electron entering the hardness box not have a defined value for hardness? After all, it's coming out of a hardness box. Shouldn't that imply for sure that the electron has a hardness when it enters the final hardness box? And what we're going to see is although these white electrons enter a hardness box, this device, this interferometer, is actually not making a measurement of hardness. So we'll have to come back and see exactly why that is. Okay, so we're going to build another experiment using the hardness interferometer. And this time, instead of measuring hardness at the output, we're going to measure color. And also, instead of injecting 100 white electrons, we're going to inject 100 hard electrons, okay? When we do this experiment, what we find is that at the output, we have half of the electrons exiting the blue port and half exiting the white port. Now, an explanation for this, which is perfectly reasonable, is that these hard electrons enter and take the hard branch, so they remain hard because we already know they're hard. We're remeasuring hardness, so we're going to get hard 100% of the time. And then we have 100 hard electrons entering this color box, and we know that a hard electron entering a color box has a 50-50 chance of exiting either of the two color ports. Okay, it turns out that explanation is mostly right, but there is a bit of a problem with it, and it's a subtle issue. We'll come back to it in a little bit. For now, I'll just say that explanation requires us to assume that all of the electrons took this H path. Okay, but what you got to remember is that this whole apparatus is basically boxed up. It's got one input and it's got one output, and we're not looking in the box. Okay, so we don't know, we don't have direct information, we don't have a measurement of which path was taken through this interferometer. And if we don't know which path was taken, then we are not making a measurement of hardness, because by definition, measuring hardness is going to separate out spatially the hard from the soft electrons. Okay, but we don't know how that happened because we're not allowed to see in the box. All we see is all of the electrons exiting out of the interferometer's exit port, but that doesn't tell us which branch was taken. So if we're not making a measurement, then it's as if that device were not even present, right? One way to not make a measurement is just to have the electron go through space and not enter a hardness box. Another is to go into a hardness interferometer and with recombined outputs. And if those two are really equivalent, then you can effectively get rid of the interferometer. Okay? So that takes us to the more correct explanation in this experiment, which is we shoot 100 electrons in to a device that does not measure the properties of those electrons. So those electrons appear at the exit port in exactly the same state that they had at the input. And then we can say, okay, we have 100 hard electrons entering a color box. We know that every one of those electrons has a 50-50 chance of emerging blue or white, and therefore we're going to have 50 blue and 50 white at the output. Now, you might be wondering to yourself, well, the two explanations that you just gave sound awfully similar, right? In both cases, you end up with 100 hard electrons entering the color box. But there's a very important difference, which we're going to uncover when we talk about the next experiment. Okay, guys, brace yourself. This is experiment number 6, and this is where we can start to distinguish between all of the explanations that we've been given so far for the experiments 4 and 5. Okay. Here we send 100 white electrons into the hardness interferometer. Okay. And we measure color at the output. And quite to everybody's surprise, instead of having 50-50 at the output, we have 0 blue and 100 white. Okay. So why is that bizarre? Well, if we have 0 blue and 100 white, that's telling us that we did not have electrons with a defined hardness state at the exit of the merger box, because if we had electrons with a defined hardness state here, then the output of color would be 50-50, right? If you shoot a hard electron into a color box, it's a 50-50 exit probability. If you shoot a soft electron into the color box, it's 50-50. So if you have a defined state of hardness at the entrance of the color box, you're going to get 50-50 output, but we do not. In fact, we can do better than saying that the electrons don't have a defined hardness state at the exit of the merger box. We can say that we know the electrons are in the white state, right? Because when we measure color, we get white 100% of the time. So in sum, at the exit of the merger box, which is the same as the entrance to the color box, the electrons do not have a defined hardness, but they do have a defined color, and that color is white. So why is that bizarre? Well, these electrons have just exited a hardness box, so doesn't that constitute a measurement of hardness? And it turns out, perhaps surprisingly, that no, the presence of the hardness box does not constitute a measurement of hardness, because we still do not have which way path information because of the merger box. Okay, so the hardness box does not guarantee a measurement of hardness unless we know or measure which path was taken through the interferometer. Okay, so what we can say here is at the exit of the interferometer, the electrons are in a superposition of hard and soft, and it turns out that that superposition is equivalent to being white, to having a defined color. Another perhaps more straightforward way to say this is we shoot in 100 white electrons, and out of the merger box, we're getting 100 white electrons. So this unblocked, unwatched interferometer has no impact on the state of the electrons. So an unblocked, unwatched interferometer has no impact on the electron state, which means that exiting the merger box at the output there, we still have 100 white electrons. So this is the weirdness. This is the weird part. We're shooting white electrons into a hardness box, but those electrons emerge with a defined color and not a defined hardness. Okay, so let's look back at experiments 4, 5, and 6 together and try to come up with an explanation for what's going on here. We had introduced this mixed state explanation for experiment 4, where we shoot in 100 white electrons, half of them take the H branch, half of them take the S branch, they recombine, and here we have, at the exit of the interferometer, we have 50 H and 50 S, and so of course, those 50 hard electrons are going to exit the hard port, and the 50 soft electrons are going to exit the soft port. Seems sensible, unfortunately incorrect. Okay, what we just learned is that this unwatched interferometer does not have any impact on the state of the electrons. So when these electrons exit the merger box, they are in the same state they were at entry, which is white. Every single one of the electrons at the exit of the interferometer is white. And so now we explain this output of 50-50 in the following way. We say we shoot in 100 white electrons, they remain white, and if you shoot a white electron into a hardness box, we have a 50-50 probability of exiting hard or soft. Okay. The same thing is going to hold here. We start with 100 hard electrons. By the time those electrons make it out of the merger box, they have not changed their state because the interferometer is not blocked. There's no blockage in one of the arms, and we're not monitoring which path was taken. So we put in 100 hard electrons, we get out 100 hard electrons, and every single one of those hard electrons has a 50-50 chance of leaving the blue or the white port. So as a result, we'll get a total of 50 blues and 50 whites. Okay, now in experiment 6, again, you may be tempted to say that if a white electron enters this interferometer, there's a 50-50 chance of taking each path. So we would expect to see at the output 50 hard and 50 soft electrons. But if that were the case, then each one of the 50 hards has a 50-50 probability of exiting blue or white, and the same is true for the softs. And so you would expect 50 blue and 50 white. But we don't see that. We see 0 blue and 100 white. So this explanation of 50 hard and soft at the exit of the merger box cannot be true, cannot be correct. The fact that every single one of the electrons exit the white port tells us that we must have exactly 100 white electrons at the exit of the merger box. But how can the electrons remain white even though they've gone through a hardness box? And the reason is, although they've gone through a hardness box, the merger box rescrambles the which way path information. And so no measurement of hardness has actually been made because we do not know which path was taken through the interferometer. And in fact, to say it more correctly, each electron was in a superposition of taking both branches. Okay, no given electron took branch 1 or branch 2 because we didn't know that. And if we didn't measure which branch was taken, then we do not have a measurement of the property hardness. Okay, so to try and get at the underlying reasoning behind the various explanations, let's make a modification to experiment 6. In experiment 6, right, we had 100 white electrons into the hardness interferometer, measured color, and we found it was 0 blue, 100 white. This time, we're going to insert some blockage in the soft path of the interferometer. So what does that mean? If an electron were to exit the soft port, it would be absorbed and it would never make it even to get into the final color interferometer. Well, in that case, if we see an electron at the exit of the merger port, we know something about which path was taken because that electron could not have taken the S path, right? Because that's a blocked path. So what that tells us then is that every electron that makes it out of this box will be in the hard state. Okay, so we'll have some number of electrons here and they will all be in the hard state. Well, how many are we going to have? Well, if you shoot 100 white electrons into a hardness box, you would expect half of them to take each leg on average. If you put a wall in the S branch, then the 50 electrons that would have taken that branch will be blocked and you are removed from the pool. And so instead of having 100 electrons at the output, we are only going to have 50 electrons at the output, but they are all hard. Now, if you have a hard electron at the output, you have a 50-50 chance of making your blue or white measurement for color. Okay, so half of 50 is 25, and so we send in 100 white electrons, we lose half make it through, and of those, half exit the blue port and half exit the white port. And so we see now a distinction between an unblocked and a blocked interferometer. We saw that in an unblocked interferometer, experiment 6 showed us that no measurement of hardness was made. But here we're blocking one leg using this wall, and in doing so, we know which path was taken by the electrons that survived, therefore we have made a measurement of hardness. Okay, in this case, all electrons that exit the interferometer are in the hard state. So let's rehash something kind of interesting here. Let's look at the blue port and the exit of the color measurement box, okay? In experiment 6, 0 of these 100 white electrons make it out of the blue port, okay? But in experiment 7, that number of 0 has increased to 25, okay? And yet, we've increased the transmission in this blue port, even though we've reduced the overall transmission from 100 down to 50. Okay, so by blocking one path and reducing the number of ways an electron can make it through the system, we have increased the number of electrons exiting the blue port. And remember, we saw this with the two-slit experiment. We saw that with both slits open, you get a diffraction or interference pattern that includes a lot of dark spots as well as bright spots. And if you cover one of the two slits, that dark spot becomes brighter. So by reducing the number of ways for light to make it through the system, you actually increase the transmission in certain locations. That's exactly the same thing we're seeing here. And remember what we said, that if we increase blockage and that leads to increased transmission, then that's evidence for some underlying interference or wave-like behavior. And that's exactly what's going on here. We have some interference effects, some superposition, which makes the quantons behave in a wave-like way that leads to this enhanced transmission despite increased blockage. So here are the main takeaways that I take away from the experiments we just looked at. Okay, each path of a hardness interferometer corresponds to a value of the hardness property, either hard or soft. So there's a hard branch of the interferometer and a soft branch of the interferometer. But an electron that exits an unwatched and unblocked interferometer is in a superposition of having taken both paths. And therefore, an unwatched, unblocked interferometer actually makes no measurement of hardness if it's a hardness interferometer. What that means is, if no measurement has been made, the state of the system hasn't changed. So the state of the electron at the output of the interferometer is the same as it was at the input. And if that's true, then removing the interferometer doesn't change the outcome, right? If input and output are the same, then you can get rid of the interferometer. It's as if you just shoot the electrons through free space with no devices. You're just not changing its state. Okay. The other thing we saw with the final experiment is that if you do block one path of the interferometer, then the electron must take the other path. And if it must take the other path, you therefore know which port it emerged from in the hardness box. So for example, if we block the soft branch, we know that the electron has taken the hard branch to get out of the interferometer. If you knew which path was taken, then that's equivalent to have made a measurement of hardness, because if you know what path was taken, you know the hard property of the electron. Okay, I will close with the following idea, namely that we can box up this interferometer just to make it easier to draw these things schematically. And so if we have, say, a hardness interferometer, we have an input and one output, one in, one out. Okay. Inside these boxes, we have a hardness box with the mirrors and a merger box, and we have the hard branch and the soft branch, and those merger boxes bring us to a single exit. We don't have to draw all of the innards. We can just draw on the outside one input, one output. We'll label it with a big H for hardness interferometer, and then we'll acknowledge that there's two paths through this system, H and S. And we're going to draw this in two boxes because we're going to allow ourselves the ability to insert something that blocks the H branch or that blocks the S branch, and so on. And of course, we can do the same for a color interferometer, one input, one output, color box, two branches, merger box. Drawn more abstractly, one input, one output, a big C representing color interferometer, and then W and B labeling the two branches that you can take through the interferometer. And so let's just make sure that we understand what's going on here. And let's do the following example. We have a hardness interferometer followed by a color interferometer, and we're shooting one single white electron into this device, but we are blocking branch 2W. So I'm going to put an X here, meaning that that path is blocked. Now I just want to say a few words about this labeling, 1H, 1S, 2B, and 2W. Here the 1 just means first interferometer, and the 2 means second interferometer, and H and S means the hard and the soft branch of the interferometer, and B and W means the blue and the white branch. We label it that way, though, just so we can identify very easily which branches are being blocked and which is open and so on. But that's all this nomenclature means. Okay? And let's just kind of march through and answer these questions. Okay? Our goal is to find the probability that a single white electron exits the interferometer given that 2W is blocked. And we're shown here in this nice table. Each column represents the state of the system at various locations along the way. Okay, so we're blocking branch 2W. Our input state is white. Okay, what branch is taken through the hardness interferometer? Well, we don't know because it's an unblocked interferometer. So it's unblocked. So the electron took a superposition of both paths. Okay. If that's true, then this interferometer does not affect the state of the electron at all, so the intermediate state here is the same as the input state. In that case, the input state is white, therefore the intermediate state is also white. Okay, now we come to the color interferometer, but it is a blocked interferometer, or at least it's partially blocked. If branch 2W is blocked, that means the electrons must take 2B. So we know that the electron here must take path 2B to the output. Okay, so that tells us that the output state is blue. Okay, but we said before that this intermediate state is white. Okay, this white electron 100% of the time is going to try to take the white branch, right? But that branch is blocked. So what is the probability of making it through this system? It's 0%, 100% blockage, because every single electron that comes into the hardness interferometer exits in the white state. It then enters the color interferometer and 100% of the time tries to take 2W, branch 2W, but it's going to be blocked because we blocked that branch. So there's nothing making it to the output. Okay. So all of the electrons go this way, and they are all blocked. Therefore, none of those electrons make it to the output. So we could also update our table here instead of saying that the output state is blue, we could say not applicable because there are no electrons at the output. That said, if we change the setup so that instead of shooting white electrons into the apparatus, we shot blue electrons into the apparatus, then those blue electrons would remain blue after the hardness interferometer because it's unblocked and unwatched, and all of those blue electrons would take the blue path and make it to the output. So in that case, if you put a blue electron into this apparatus, the probability of transmission would be 100%, and the output state would be blue. Okay, well, I hope that this video has given you a sense for interferometers, what they do and what they don't do, and in particular, the key takeaway point is what we saw before, that an unblocked, unwatched interferometer makes no measurement and can be removed from the system without changing the outcomes. Okay, well, that's it for now. Until next time, take care, be well, and have fun. All the best.